Welcome to SolarSTEAM here at the Southern Illinois University in Carbondale. I'm your host for today, Chisom Ndiorji, and I'm here with Doctor in Physics and faculty member here,
Chris Mandrell.
Thank you. Would you like to tell us a little bit about your role here at the university?
Here at SIUC, I spend a little bit of time as a faculty member teaching some 200 level physics courses, but I spend most of my time as a project coordinator for the Dynamic Eclipse Broadcast Initiative.
Thank you. So today, Dr. Mandrell is going to tell us a little bit about the different phases of the solar eclipse. So I've heard that you're involved in astrophysics. Can you define that briefly for us and tell us how exactly you got involved in it?
So my involvement in the physics, where we would call that astrophysics, is based around heliophysics specifically, where the group that I'm associated with studies the dynamics of the photosphere of the sun. We're looking at how things interact, magnetic fields, electric fields, particle accelerations, decelerations. And that's with our local star, the sun. When you talk about astrophysics in general, now you're going to be talking about how things on a grander scale, out there, the stars in our galaxy and other galaxies and the solar system's formation of these things, studies of exoplanets and all of that. So it's a very broad field. But what I specifically have been looking at so far is the dynamics of solar flares, energetic events on the sun, and how those things, how we can describe those with the tools we have in physics.
Interesting. Well, you probably already know this, but there is an upcoming eclipse this August in Spain. And can you talk to us a little more about that eclipse and your role specifically as a member of SolarSTEAM?
So the eclipse in Spain is exciting because it's a total solar eclipse, which is probably the most exciting type of eclipse that there is. So you have a great opportunity for outreach. It's on the other side of the Earth there, so we're reaching a different group of people to get to see this than we have when we have these North American eclipses that we've been dealing with the last few years. But it's also interesting because it's a sunset eclipse. So the eclipses that we've had here the last several years have all occurred around midday or so, and the sun's been and the moon have been very high in the sky. Great for collecting data, imaging. We've had long paths of totality, so we've been able to get a lot of teams looking so we can capture the evolution of the sun over a couple of hours. This eclipse in Spain is going to be beautiful because it's going to be on that horizon. So the perspective of it will be different. Have you ever noticed how when you look at the moon as it's rising or setting, it appears quite large compared to it does when it's up in the sky? Similar, it's the perspective. You have frame of reference with the horizon, so it makes your brain, look at things a little differently, process things a little differently. And we'll have a similar effect with this one because the sun-moon system will be close to the horizon. It's not going to be as scientifically relevant because when we're looking that low on the horizon, we have to look through really long run of our Earth's atmosphere. The light has to travel through clouds, water, vapor, different gases that are in our atmosphere. And that causes wiggling of the light and things like that make it a little more difficult to get solid scientific data, but it'll be truly inspiring in its beauty. And it's a great opportunity for us to test out our equipment and our new programs that we're going to use and everything for eclipses in the future that will be more scientifically relevant for us.
Wow, thank you. You said, from what I understand, that this one will be more aesthetic.
Yeah.
Now, everyone knows you need eclipse glasses to safely look at a solar eclipse. Can you walk us through the science behind that and specifically why exactly totality is an exception for that rule?
Yeah. So the sun that we're seeing when we look up in the sky, the surface of the sun is the photosphere. And it is incredibly hot plasma that's emitting tons and tons and tons of electromagnetic radiation. And a lot of that radiation gets filtered, the bad stuff gets filtered out by our atmosphere and things like that. Or we put sunblock on to keep us from getting sunburn, things like that. But you don't ever look directly at the sun because there's so much light, so much radiation coming from there that it will actually burn parts of your eyes. It will cause you vision problems. It can cause serious problems. And this is, if you've ever looked at the sun and then you look away, you just have this imprint of the sun wherever you look and you can't really see stuff around you. Just from that quick dose, you got this imprint and you're like, oh my gosh. And your brain knows not to do that, not to look at that thing, that really bright thing in the sky. But as an eclipse occurs, the moon blocks more and more and more of the light coming from the sun being emitted by that photosphere. And it reaches a point where it's comfortable for us to just sit there and stare at it. And our brain's not, oh, that's painful. Oh, that's not good. But we're still getting that high amounts of electromagnetic radiation, light from the sun that's hitting the back of our eyes. And it's still energetic enough that it's doing damage. So the problem with eclipses really lies in the sun's not any more dangerous during an eclipse than it is on a day-to-day basis. But your brain thinks you can just sit there and stare at it because it's not painful anymore. So now you'll actually just, oh, isn't that beautiful? And you're letting all of that light hit the back of your eye and do serious damage. So that's where the real danger is your brain's convinced, oh, this is fine. Look, it's pretty. And you're looking directly at way too much light to be hitting your eyes.
I think that was a very good explanation because I personally didn't understand that much. Can you tell us a little more about the general timeline of a solar eclipse, like the progression of phases, some of the phenomenon, and if you have any favorites too?
Okay. So, excuse me. So an eclipse, just to be clear, I just for props, I brought my own moon here because we have a globe that's the Earth. And if we imagine somewhere back behind the cameras and everything, the sun's very, very far away. Where this sun's at in this system, the Earth would be actually orbiting out that way from, the viewers would be seeing it pass off to the left. And that's how we have our years. The Earth orbits the sun, and it's got this tilt to it, and that's why we have seasons and everything like that. But we go, as we look down, counterclockwise around the sun. And then we also have, that's our year, we have our days, and that's where our Earth spins on its axis, and it does this once every 24 hours. It spins around, so 365 days to go around the sun, 24 hours to spin around the Earth, and that happens counterclockwise as well. Well, the moon is going around the Earth counterclockwise. So as we look down from the vantage point of the North Pole down on our solar system, everything's going counterclockwise. And so the moon's coming around, and it takes about 30 days to do this. And every once in a while, it lines up to where the moon falls directly in between that sun out there and some portion of the Earth and casts a shadow. And so that's what a solar eclipse is. And the interesting thing is that because this moon is traveling around, it takes 30 days to go around the Earth, and we're rotating on our axis 24 hours. You would think that, this spinning would be faster than what's going on here. And this will all make sense when I get to the point of this. But out here, this moon is actually traveling faster than, say, someone just on the equator of the Earth. Even though this takes 24 hours and this takes a month, this is traveling a little bit faster because it's further away to go around the same spot. So what that means is that the reason I point that out is because when we look up in the sky at night, we see things, or even during the day with the sun, we see things rise in the east and set in the west. They always do. Things rise in the east, they set in the west. As you look out, as time passes overnight, you see the stars move from east to west in the sky. But with an eclipse, what we'll see is that the shadow of the sun, or the shadow of the moon crossing in front of the sun, will actually move across the Earth from west to east, which is backwards of how all that's happening. And the reason that does that is because of this fact that this moon is moving really fast out here. And there's the geometric relationships get a little complicated, but the effect is that the moon is moving across the surface of the sun as we look at it here in the northern hemisphere from the right to the left. So when you look up right at the beginning of an eclipse, or we call it first contact, where the moon first casts a shadow, first blocks part of the sun, it'll happen on the right side. It'll be blocking the sun on the right side as we look up. We call that C1, and when you look at maps, you'll see C1 as that's the start of the partial phase of an eclipse. So we're still seeing the majority of the sun, and we're just seeing a little circle or a little arc of the moon. And that moon will continue to progress across the surface of the sun. And as we stand in one location, it'll just, the moon will obviously be moving across the surface of the sun until we reach C2, or second contact. And that's where, from our vantage point, the left limb or edge of the moon reaches the left limb or edge of the sun, and we have the beginning of totality. Now it's safe to pull those glasses off if it's a total solar eclipse. And that will last, depending on the relationship, spatial relationship of everything, from, a few seconds to a few minutes. And then the moon, which is just continuing to move on past the sun, will now start to see on the right side where we first made contact. Now we'll start to see sliver of the sun's photosphere again. And then that will continue to pass on as we go through the last portion of the eclipse. So we have C3 is where we start to see more of the photosphere again. And then we call C4 where the sun, or fourth contact, where the sun and moon actually are separated. Interesting thing about C2 and C3 is the phenomenon we call the diamond ring, which is my favorite thing. It's one of my favorite things. They're all my favorite things. But because we're caught just a little sliver of the photosphere around the moon, when you look at it through cameras, look at it safely and everything like that, because it's right at the transition where you're not supposed to be looking at it without your glasses on. It looks like a diamond ring. And some of the most fabulous pictures you'll see of eclipses are of diamond rings, put over the top of landscapes, stuff like that. But then there's also other effects that happen as we get, instead of this nice big ball of light that's illuminating all of the Earth, as we get close to C2 and C3, or as we're right at the edges of totality, there's just this little sliver of the sun that's emitting light onto us. And that causes all kinds of neat optical effects. You have the shadow that you see people. You'll see people doing all kinds of crazy stuff during eclipses where they've got their fingers crossed or they're looking under trees. And the shadows you see are actually representing that emitted light coming from the sun as a crescent. Now you see all of these crescents everywhere. So if you were to cross your fingers and look at the ground where the light from the sun was passing through your fingers, it would be a bunch of little crescents because you're seeing that point source is no longer a nice sphere. It's this little crescent. And then there's other wave light interactions that with things going on with the atmosphere and everything that people get really excited about. But those are the ones that I like, the crescent shadows and the diamond ring.
Personally, when I saw the 2024 eclipse here in Illinois, I saw the Bailey beads you were talking about. Well, that was really fascinating. And then also, I was trying to separate the solar prominence from the solar corona. I had issues with that. Could you help differentiate the two for the average viewer?
So yeah, when you look at a total solar eclipse, you will see, you'll see colors. You'll see reddish orange regions around the limb or the edge of the moon. And those are prominences. Those are parts of really dense portions of the inner corona that are extending out in space because of the magnetic field of the sun. So the plasma that makes up the sun is being pulled into space and following these paths along these intense magnetic field lines that are what are created by the sun's boiling nature of charged particles. And so those extend out past the surface of the moon. And so those are prominences. And that's the regions that you're seeing where you have the color and things. Or if you look through a telescope or you see some, online, you're looking at someone doing a live broadcast of the eclipse, you'll see these loops and prominences. You can see those when you look through a telescope with proper filtering, when you look up at the sun normally. And that's impressive because the sun is really, really bright. And for you to be able to see these things, which aren't actually the surface of the sun, they're sun stuff being ejected out of space, gives you some idea of the scale of these. They're really big, they're bright, but they're not dangerous like the full photosphere. And then you move the moon in front there, and now those really stand out. And you get the reds and the oranges and the yellows around the moon. Those prominences really stand out. And then the corona is that when you're looking with your visual eyes at an eclipse, that white light that's spreading out like web from the sun. That's the corona. That's the solar winds basically traveling away from the surface of the sun.
Thank you so much. So I heard about a predicted eclipse in 2027, actually in Morocco this time. And it's supposed to have about 5 more minutes of totality. Now, I have 2 questions about this. First, how exactly do we predict when these eclipses are going to happen so far into the future? And secondly, why are the timings of the totality so different when Spain and Morocco are like right next to each other?
Yeah. So a lot of number crunching for predicting. We know that we know what this tilt is as the Earth orbits the sun. We know how the Earth is orbiting the sun. We know that the moon is orbiting the Earth, but that it's actually got a little bit, about a 5-degree tilt to its plane of rotation around the Earth, as I'm going the wrong way. So all of those things give us the ability to do a bunch of number crunching and say, okay, in August 9th of this year, and then, so that would be, what month comes before ours?
July.
July of the next year, there's a really good chance we'll have an eclipse. June of the next year. And there's some patterns to it. So we could kind of predict on a basically an 18-month scale, in general, when we're going to have eclipses. So we're not surprised by them like the ancient humans were, because they didn't have this, they weren't really tracking time. Well, we can at least say, oh, okay, 18 months somewhere in the world, they're probably going to have some type of an eclipse. But now we can, because we understand these relationships spatially, we can just see where things are at, track them all out using computers. People used to do this by hand, but now we just use computers to track where things are at. And when the moon, sun, earth system line up, either for a solar eclipse or a lunar eclipse, we can say, okay, that's the time. And then we can get into details about where that eclipse will occur, because we'll be able to track into time, going in the future. Okay, this is where the earth will be at that time when that shadow is being cast. And we can calculate the relationships and say, okay, the shadow is going to be projected, here or here. So it's just through numerical analysis of the relationship of these things. Now, there are patterns and cycles that occur because this is a very set system. We have this angles that are all the same over time. So again, there's some periodicity to it that we can say that eclipses match certain patterns, like they'll return to certain places on different cycles and things like that. But that's down the rabbit hole of the numerical analysis. But the idea is just tracking. I know where the moon's going to be. I know where the sun's going to be in our sky based on our rotation. And I can just keep tracking that until things line up here. And now there's people that spend a lot of time doing this to where they'll even, figure out, this is your elevation. Not just you're on Earth at this latitude and longitude, but this is your elevation because you're on this mountain, or you're in this depression and you're surrounded by mountains. So this is what you're going to see, and they predict even that much of detail of it. So it's just how precise you want to be in your calculations. We are able to predict all of these things.
Really fascinating process here. Thank you again for coming today, and thank you for your time. And I'd like to thank you all for tuning in here at SIUC SolarSTEAM. Be sure to visit our website at solarsteam.siu.edu for more information about what we do and the kind of things we record here. Thank you so much.
Thank you.